In an earlier lecture where we introduced ideal voltage sources and ideal current sources, we briefly talked about batteries being non-ideal in the sense that when current is drawn from the battery, the terminal voltage drops somewhat. In today's lecture, we're going to look at this in more detail by modeling what we call practical sources, practical voltage sources and practical current sources. We're then going to take those practical source concepts and introduce a circuit analysis technique called source transformations. So let's start by talking about practical voltage sources. In an ideal voltage source, the voltage across the terminals of the source depend only on the voltage source value V, regardless of what that source is connected to. In the real world, however, the voltage across the terminals of a source are going to depend somewhat on the current that's being drawn from the source. Specifically, we're going to see that as we increase the current being drawn from the source, the voltage at the terminals of the source will decrease. We can model this mathematically by taking an ideal voltage source and putting a resistance in series with it. So you take an ideal voltage source and you put a series resistor with it. This series resistance is called a source resistance and is typically very small. If you look at the VI characteristics now at the terminal of this practical source, what you'll see is that the voltage V, which is what we call the terminal voltage, is related to V naught, which is what we call the nominal voltage, by this expression here. The terminal voltage is the nominal voltage minus a voltage drop across this internal source resistance. So this internal source resistance R naught has a voltage drop across it from Ohm's law equal to R naught times I, which is the current coming out of the source. So this voltage is R naught times I. So once again, if we do KVL, we get minus V naught plus R naught I plus V is equal to 0, or the terminal voltage is equal to the nominal voltage minus R naught times I. If you plot this on a VI plot, you'll see that for an ideal source, the terminal voltage is going to be constant, and it would equal the nominal voltage. So once again, this is the nominal voltage. But in practice, what we're going to see with a real source is that the more current you're drawing from the source, the lower the terminal voltage is. This phenomenon is known as the loading effect, and in general, it is something bad that you need to deal with. The slope of this line, by the way, is equal to minus R naught. So if R naught is very small, which it typically will be, you'll see that this slope is not very steep. So it takes a while for this voltage source to look non-ideal. Nevertheless, this loading effect is something that we do need to take into account in the real world. The other thing we're going to see in some examples is it's very dependent upon what we're connecting up to this source. So you have a load resistance RL there. The higher RL is, the less current you have, which means the less voltage drop you have internally, which means the closer the terminal voltage is going to be to the nominal voltage. One final point before we continue on with an example is this point on the graph here is what happens if you short out the voltage source. In other words, if you connect these two terminals together so that the terminal voltage is 0, what happens is you get a very high current equal to the nominal voltage V naught divided by the internal resistance R naught. And we call that short circuit current. This is going to play a part later on. Let's do a simple example. So let's say we have a practical voltage source. So this is a practical voltage source. It has a nominal value of 10 volts, so we call it a 10 volt source, but it has an internal resistance of about 0.1 ohm. And we want to determine the effect of the source resistance on the terminal voltages when we connect up two different loads. So what we're going to see is the voltage across the load VL is equal to what? It equals the load resistance divided by the load resistance plus the source resistance times the nominal voltage. So VL is going to be RL over RL plus R naught times 10 volts. So let's look at two different load resistor values, 100 ohms and 8 ohms. If the load resistance is 100 ohms, what do we get for the voltage across the load? VL is going to be 100 over 100 plus 0.1 times 10 volts. You work out the math, it's 9.99 volts. In this example, we have very little loading. The voltage we get at the terminals, 9.99 volts, is very close to the voltage we expect, 10 volts. However, if the load resistor is only 8 ohms, its voltage is going to be 8 over 8 plus 0.1 times 10 volts, or 9.87 volts. So in this example, there's more loading. Once again, the voltage you get is quite a bit less than the voltage that you expect. What we're going to see in general is that the smaller the load resistance, the more current you're drawing from the source, which means the larger voltage drop across the internal resistance in the source, which means there's less voltage available across the terminals of the source. And once again, this is called the loading effect. It in general is a bad thing that we need to deal with and we need to be aware of. What we want, typically we want the load resistance to be much, much larger than the source resistance to minimize loading. Well, let's look at current sources now. So once again, in an ideal current source, you have a nominal source value I. You have these terminals here. And the current coming out of the ideal current source is a function only of the nominal current value. No matter what you hook up to the circuit here, the current coming out of the source is going to be I. However, in practice, what we're going to see is as you hook up loads, the terminal current is not going to be identical to the nominal current. It's going to be a little bit less. The way we're going to model a practical current source is with an ideal current source in parallel with an internal resistance R0. So once again, this is our nominal source value. This is what we call an internal resistance. This current I is what we call the terminal current. That's a current that's actually available to drive the load. And we're going to see that the relationship between the terminal current I and the nominal current I0 is given by this expression here. Because of this internal resistance R0, there is going to be an internal leakage current of what? The leakage current is going to depend upon the voltage across the load V. So the current through R0 is going to be V over R0. So doing KCL at this node, we get minus I0 plus V over R0 plus I is equal to 0, or I, the available current, is equal to the nominal current minus this lost current. So this V over R0 is this current that's lost internally to the device. We can show this on a VI plot as well. In an ideal current source, there is no R0 at all. And so it's going to be a vertical line. Regardless of what the voltage is across the source, you're going to get a current of I. In practice, what we're going to see is the larger the voltage is across the load, the less current you're going to get. So the larger the voltage, the less current. In an extreme situation, suppose we connect nothing up to this load. We call this an open circuit situation. Now, all of the current being generated is going to go through the internal resistance, and the voltage at the terminals is going to be what? I naught times R naught. We call this the open circuit voltage. The slope of this line is equal to minus R naught. In a current source, typically R naught is going to be very large. So this is going to be a nearly vertical line, which is good because it's going to be close to what we want ideally. But unlike an ideal current source, we will see that as you have more voltage across the load, you're going to have more current lost internally, which means less current available to actually drive the load. So let's look at an example of a practical current source. So let's say we have a practical current source, and we're going to model it mathematically as a 1 milliamp ideal source in parallel with a fairly large internal resistance, 50 kiloohms. Once again, with current sources, this internal resistance is very, very large. With voltage sources, that internal resistance is going to be very, very small. So let's connect two different load resistors, a 100 ohm and a 10 kilo ohm resistor, and see what the actual current through the load is going to be. So from current division, IL, which is the load current, is what? The current through the second resistor is equal to the other resistance, in this case 50 kilo ohms, divided by the sum of the two resistances, 50 kilo ohm plus RL, times the current source value, 1 milliamp. So that's the equation from current division. So when RL is equal to 100 ohms, what do we get? The actual current through the load is going to be 50,000, the other resistance, over the sum of the two, 50,000 plus 100 times 1 milliamp, or 0.998 milliamps. So once again, the available current to drive the load is a little bit less than the nominal value. And once again, we call this loading when we see that there's a little bit of loading. But what happens now when we have a larger load resistance? When RL is equal to 10 kilo ohms, its current is going to be 50,000 over 50,000 plus 10,000 times 1 milliamp, and we end up getting 0.833 milliamps. Here, you see a much bigger difference between the current you actually get through the load and the current you want through the load. So this one has more loading. So we see an opposite effect as what we see with real voltage sources. As the load resistance goes up, there's going to be a larger voltage drop across the load resistance, which means there's going to be a larger voltage drop across the internal resistance, which means there's going to be more current lost internally and less current available for the load. So this is also loading, but it has the opposite effect as with voltage sources. In fact, with current sources, what we want the load resistor to be much, much less than the internal resistance to minimize loading. So once again, in a practical voltage source, R naught is going to be very small, and we want the load resistance to be much larger than R naught to minimize the loading. In a practical current source, R naught, which is a parallel resistance, is going to be very, very large, and we want the load resistance to be much less than R naught to minimize the loading. So practical sources are an important concept all by themselves, because in the real world, when you have practical sources, even if that internal source resistance for a voltage source is very, very small, and even if the internal source resistance for a current source is very, very large, you still need to take them into account when designing your circuits. But practical sources have another purpose as well, and that is the concept of source transformations. And this is covered in the book in section 4.9. If you look at the VI characteristics of a practical voltage source, you see that it has a shape that looks like that. If you look at the VI characteristics of a practical current source, you'll see that it has a shape that looks like that. And one thing you note is that although an ideal voltage source and an ideal current source look nothing alike, a practical voltage source and a practical current source can have the same shape. And that is a concept behind source transformations. If you have a voltage source and a series resistance connected up to a circuit, that circuit doesn't know the difference between a voltage source and a series resistance and a current source and a parallel resistance. As far as this pink blob is concerned, it sees the same shape, provided that the relationship between I naught and V naught is as follows. So if you take a voltage source and a series resistance, take V naught divided by R naught and turn that into I naught, and take this R naught that's in series here and put it in parallel, you get the same VI characteristics as far as the rest of the network is concerned. You could go the other way as well. If you start off with a current source and a parallel resistance, if you take I naught, multiply it by R naught to get V naught, you could then convert a current source and parallel resistance into a voltage source and series resistance. This is a concept of source transformations. We're going to see that by transforming this to this, or vice versa, can sometimes make your analysis easier. Need to explain here, we are talking about doing this analytically only. We are not saying that we're physically going to replace a voltage source by a current source or physically replace a current source by a voltage source. One of the reasons is, remember, this R naught here in a real voltage source is going to be very, very small. This R naught here in a real current source is going to be very, very large. So if you convert physically a voltage source to a current source, this R naught here would become a very small R naught, which you typically are not going to have in a current source. So source transformations are an analytical tool only to help you in analyzing a circuit. It is not something you would physically be doing. Just wanted to make that clear. We're going to do an example in a couple slides. But before we do that, we need to make an important observation. And that is that when you do the source transformation, the power being delivered by the source changes. For example, let's look at a practical voltage source with open circuit loading. In other words, there's no load attached here. Because there's no current flowing out this terminal, the actual power being delivered by this source is zero. If you do a source transformation, convert this voltage source and series resistance to a current source and parallel resistance, what you're going to see here is you're going to get current flowing through this resistor, and that current actually is what? V naught over R naught. So the power being absorbed by that resistor is its value, R naught, and I missed the naught there, times the current squared. The current is V naught over R naught. Likewise, if you look at a practical current source where you short the terminals together, if you then analytically replace it by a voltage source, what happens to the power? In the current source case, we now have 0 watts being absorbed because the voltage across R naught is going to be 0. In the voltage source case, the power is not going to be 0 because the voltage across this resistor is what? R naught times I naught. So its power absorbed is R naught times I naught squared, and once again I forgot the R naught in there, the voltage squared divided by the resistance, which is just I naught squared times R. So what we see is that the power delivered by this voltage source and this current source are not the same, and we see that the power delivered by these two sources down here are not the same. And this actually would be true not just with open circuit and short circuit loading, but you put any load resistor in there practically and you're going to get different power values. So this gives us an important result, is that source transformation is not useful if you are looking to find the power delivered or absorbed by a source. So bottom line, If you are interested in another part of the circuit, you could use source transformation to help your analysis, as we're going to see in a couple examples. But if you are ultimately interested in the source itself, you do not want to do source transformations, because source transformations will mess up the power being absorbed or delivered. A couple more comments before we get to examples. One of these is sometimes you can do source transformations where it's not as obvious. This especially happens when you have these interior branches. For example, suppose you have a circuit here. Then within the circuit you have a current source and a parallel resistance. This, of course, would be the model of a practical current source. Well, from this figure on the left, you can go to this figure on the right. From this figure on the right here, you can go to this figure down below. And so you can turn the current source and a parallel resistance into a voltage source and a series resistance. And then from there, you can redraw it on the left. So we see if you have a current source and a parallel resistance, you can replace it by a voltage source and a series resistance, even if it's in an interior part of a circuit. A common mistake is sometimes people see this and think, oh, I can do source transformations, and they try to do something like this. They say, okay, the current source can be turned into a voltage source and a series resistance. Voltage source of value what? R times I naught. Keep that same value there. And they try to do that. Once again, they're thinking, we're taking that and doing a source transformation. This is not correct, though. Although you can convert the current source to a voltage source, notice where this resistor has to be. The resistor has to be here, not over here. So if you think about these 4 connection points there, 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 and there, it corresponds to that point, that point, that point, and that point without that resistor here. Another important point is with dependent sources. You can do source transformations with dependent sources, provided that you're not altering the controlling voltage or current when you do the source transformation. So remember, you always have these controlling variables here. As long as those variables themselves are not messed up by the source transformation, you can take, for example, a voltage-controlled voltage source and turn it into a voltage-controlled current source. Likewise, you can take a current-controlled current source and turn it into a current-controlled voltage source. You can do that with the other 2 types of sources as well. So bottom line, you can do source transformations with dependent sources as long as you don't mess with the controlling variable when you do the transformation. At this point, source transformations may seem a little complicated, but they really are not hard at all. And I think once we do a couple examples, we'll see that it's a very simple tool that can be helpful in some circuit analysis problems. So if we look at this problem, we're asked to determine the power absorbed by the 2 ohm resistor, and we're told in this problem to use source transformations to simplify the rest of the network. First thing I want to say here is that you do not have to use source transformations to solve this problem. You could do the ad hoc circuit analysis approach to try to fumble through and find the answer. You could do nodal or mesh analysis, techniques we have not learned yet, to solve this. Could you do things like source and resistor combinations, however? Your first inclination would be, yeah, you could combine that 20 ohm and 2 ohm resistor in parallel to simplify the circuit. The problem is we're looking for the power absorbed by the 2 ohm resistor. And if you remember the general rule of thumb, when you're looking for information about a specific component, you typically do not want to combine that component with other components. Secondly, even if we combine the 20 ohm and 2 ohm resistor in parallel, we're sort of stuck there. There's really no more simplification we can do. So although you could use an ad hoc analysis to solve this, and although you could use nodal and mesh analysis, you could not do things such as just resistor combinations or source combinations to solve this problem. But we're going to see that what we can do is use source transformations to solve this problem. This is the part of the circuit that we're interested in. We're interested in the rest of the circuit only in the sense that we want to see how it affects that 2 ohm resistor. That means that everything on the left here we can possibly change around if we want, if it helps us get to the final goal of finding the power absorbed by the 2 ohm resistor. So if you think about it, we have a current source and a parallel resistance. So one approach would be to convert that to a voltage source and a series resistance. And this is one of the situations where this is an internal situation. If you go back a couple slides, that's the situation here. So we could convert that current source and a parallel resistance to a voltage source and a series resistance. But if you think about it, that actually doesn't do us any good. The other thing we could do is recognize that we have a voltage source and a series resistance and convert that to a current source and a parallel resistance. And that actually will do us some good. So let's try to do that. So we have this 20 volt source and a series resistance of 5 ohms. So we're going to mathematically replace this by a current source and a parallel resistance. So the current source value has to be 20 volts divided by 5 ohms. When you do source transformations, the value of that current source is going to be 20 volts divided by 5 ohms, or 4 amps. And it's going to have a parallel resistance, and that resistance is the same value, 5 ohms. The other important thing is figuring out which direction the arrow should go. The way to figure that out is you look at this voltage source. It wants to push current out this top terminal. So when you convert it to a current source, you want to choose the current arrow so it pushes current out the same terminal. So you put the arrow going up. What this is saying is, as far as the rest of the circuit is concerned, that and that are the same. How this is useful then is if we put this back into the original circuit with this source transformation, 4 amp, 5 ohms, stick that back in, so we still have this 2 amp source here, and we still have this 20 ohm resistor here. And then, of course, our load resistor, which is the thing we're concerned about, right there. But what we see, by doing the source transformation, we can now go a step further, because we now have 2 current sources in parallel, and we have 2 resistors in parallel. Technically, we have 3 resistors in parallel. However, we don't want to combine the 2 ohm resistor because that is what we are ultimately interested in. So if we do these combinations, the 4 amp and the 2 amp current sources become a single 6 amp source. The 5 ohm and 20 ohm resistor in parallel, 5 in parallel with 20 is 4. Where does that come from? 5 times 20 over 5 plus 20. Then we can connect that up to our load resistor RL. But now we're at a point where we can use current division. So we can now find the current through the 2 ohm resistor, call that I sub 2 ohm. So from current division, the current through a resistor is equal to what? Because there are 2 resistors, it's the opposite resistance, 4 over 4 plus 2 times 6 amps. So I sub 2 ohm is 4 ohm divided by 4 plus 2 times the total current, or 4 amps. Once you know the current through a resistor, you could find its power. The power absorbed by the 2 ohm resistor is what? I squared times R. So 4 squared times 2, 32 watts. So what we see here is that the source transformation, converting this voltage source to an equivalent current source, then allowed us to then do some source combinations and resistor combinations to finally get to a point where we could use current division. Once again, I want to stress, this is not the only way to get this final answer, but of all the different techniques we learned so far, it's really the only one that works easily. Let's do one more example. So in this example, we're asked to use source transformations to find the value of this current IS. IS is the current going through this 15 ohm resistor or this 27 volt source there. So we once again want to think about what we could do. Here we have a voltage source and a series resistance. We could convert that to a current source and a parallel resistance. However, because what we're interested in is a current coming out of that source, we probably don't want to do that. General rule of thumb, you don't mess around with components that you're ultimately interested in. So the other thing we could do is we could recognize that we have a current source and a parallel resistance. We could convert that to a voltage source and a series resistance. The problem with doing that is that that doesn't get us anywhere either. But what we can do is first combine the 20 ohm and 5 ohm resistor in parallel and then do a source transformation on that source on the right, and we'll see that we can get somewhere. So the first thing we want to do is combine these in parallel. So 20 in parallel with 5, once again, is 4 ohms. 20 times 5 over 20 plus 5. That's 4 ohms. What we can now do is take this whole thing here, convert it to a voltage source and a series resistance. So what we have a 4 ohm resistor in parallel with an 8 amp source. What source transformation tells us is that as far as the rest of the circuit is concerned, as far as this part of the circuit is concerned, it doesn't know the difference between an 8 amp source and a 4 ohm parallel resistance and a voltage source of what value? You multiply 8 times 4, you get 32 volts. And a series resistance of the same 4 ohm value. What you want to think about is what should the orientation of the voltage source be. Think about the current source. This current source wants to push current out that terminal. So the voltage source should push the current out the same terminal, which means the plus has to be on top and the minus on the bottom. So once you do that, we can now plug that back into the original circuit. So we have our 27 volt source, 15 ohm resistor here, 30 ohm resistor here, 6 ohm, 10 ohm. Now what we're going to stick in is this source transformation. 4 ohm and 32 volts. So we're basically sticking that in there. But what this is going to allow us to do now is we can now combine this 6 ohm, this 4 ohm, and this 10 ohm resistor are all in series. So we can simplify a little bit more. 27 volts, 15 ohm, 30 ohm. 6 plus 4 is 10 plus 10 is 20. 20 ohm, 32 volt. So basically everything here is identical to that. So as far as the circuit to the left is concerned, there's no difference between those two green components. What we can do now, and we'll do this on the next page, is we can do another source transformation. This thing in green here, a 32 volt source and a series 20 ohm resistor, we could convert into a current source. So going to the next page, we have a 32 volt source and a 20 ohm resistance. As far as the rest of the circuit is concerned, that is identical to a practical current source. Its value is what? 32 divided by 20, or 1.6 amps, and once again the same resistance, 20 ohms. And once again, you got to be careful about the current arrow directions and the voltage polarities. This voltage source wants to push current out that terminal, so the current source needs to be oriented to push the current out the same terminal. And where does this 1.6 come from? It's 32 volts divided by 20 ohms. We can now stick that back into this circuit here. So we have 27 volts, 15 ohms, 30 ohms. Now we're going to stick in this green thing there and there. 20 ohms, 1.6 amps. We get that. Once again, this allows us to go another step because now we have this 30 ohm and 20 ohm in parallel. We can now combine these. 30 in parallel with 20 is what? The product over the sum, or 12 ohms. So we can now take all of this thing in yellow. This thing in yellow is what? It is a 12 ohm resistor in parallel with a 1.6 amp current source. We can now convert that to a voltage source and a series resistance, another source transformation. This resistance is the same, 12 becomes 12. The voltage source value is 12 times 1.6, or 19.2 volts. It's 12 times 1.6. And once again, this current source wants to push current out the top terminal. The voltage source should have a polarity to push the current out the top terminal. This can now be put back into this circuit here to get this. 27 volt, 15 ohm, 12 ohm, 19.2 volt. As you remember, what we're ultimately looking for is this current here. We called it what? IS1. At this point, we can now combine these two voltage sources in series. We can combine these two resistors in series and then use Ohm's law to find the current IS1. So we have a 27 volt source in series with a 19.2 volt source, but if you think about the way they want to push the current, this wants to push the current clockwise, this wants to push the current counterclockwise, so they actually get subtracted from each other. So the equivalent voltage source value is 27 minus 19.2, or 7.8 volts. The 15 and the 12 ohm resistor get added because they're in series. 15 plus 12 is 27 ohms. And what we're ultimately looking for is this current IS1 from Ohm's law. We then get that IS1 is 7.8 volts divided by 27 ohms, or 0.289 amps. And that is our final answer. So this was a complicated example because we had many steps, but what we see is that source transformations can often lead to additional source transformations and other resistor combinations and source combinations that allow you to take a more complicated circuit like this and eventually turn it into a very simple circuit with just a single voltage source and single resistance, which will then allow us to use Ohm's law. The important thing to remember is to always be aware of what you're ultimately looking for, because you do not want to lose that important piece of information. And if we started this problem by transforming this voltage source and series resistance to a current source and parallel resistance, we would be losing this variable immediately and we wouldn't be getting anywhere. But doing it the way we did it, we were able to successfully solve the problem. This concludes this packet of notes and concludes this lecture. Next class, we will talk about a different way to solve circuits, and that is using nodal and mesh analysis. It is basically going to be solving circuits by setting up systems of equations without simplifying the circuit at all. Have a good day.